last. Let's look at some of the physical characteristics of bearings to understand why we see the spectral and waveform patterns that we do. Each of these bearings has individual characteristics due to its own unique physical geometry, which cause specific frequencies to appear in spectral data when a defect is present. These defect frequencies can be calculated individually for the outer race, the inner race, the cage or fundamental train, and the balls or rollers. Let's take a look at how these can be approximated using an actual bearing on a shaft. The defect frequencies are often expressed as a multiple of the turning speed of the shaft. That is, for each revolution of the shaft, how many impacts will be made due to a particular fault. This bearing has been marked so we can visually determine the approximate frequencies. If a defect is at this position on the outer race, we can count how many balls will impact the defect during one revolution of the shaft. 1, 2, 3, 4, 5, and just a little more. 5 and a fraction balls impact the outer race with one revolution of the shaft. Notice that it is not exactly 5, but 5 and a fraction. This is the key to differentiating between bearing faults and other faults, such as vane pass, which would show up exactly 5 times for an impeller with 5 vanes. This fractional energy is called non-synchronous energy. That is, it is not a whole number multiple of the shaft turning speed, like 1.0, 2.0, or 3.0 orders. An order is a way of expressing frequency. Actually, there are 3 ways to express frequency: how often something occurs per minute or CPM, per second or hertz, per shaft revolution or orders. We will focus on orders because that is a direct correlation to shaft speed. The inner race frequency can be approximated in the same way as the outer race frequency. With the reference marks lined up again, we will assume a defect at the mark on the inner race. As the shaft is turned, let's count the number of balls that pass through the inner race defect. 1, 2, 3, 4, 5, 6, 7, 8, and a fraction. We see here that the inner race frequency is also non-synchronous. Notice that the inner race frequency is 8 and a fraction, whereas the outer race was 5 and a fraction. Unless the bearing is a unique thrust design with a 90-degree contact angle, the inner race frequency will always be a higher frequency than the outer race frequency. After lining up our reference marks, the cage frequency can also be approximated by rotating the shaft one full turn. With one complete revolution, we see that the cage went less than halfway around. Cage frequencies usually occur between 0.3 and 0.47 times the shaft turning speed. A defect on a roller will also generate certain discrete frequencies, depending on how many times the roller turns over during one revolution of the shaft. With the reference marks in line again, we rotate the shaft one full turn and this time count the revolutions of the roller. 1, 2, and a fraction. This roller defect frequency, or ball spin frequency as it is commonly called, is also non-synchronous energy. In our approximations, we've shown that the ball spin frequency, the outer race frequency, and the inner race frequency are all non-synchronous energy. The cage frequency is subsynchronous energy. That is, it rotates less than 1 time per shaft revolution. Therefore, a subsynchronous frequency is a lower frequency than shaft turning speed and is a fractional order value. The cage frequency will be less than 1/2 or 0.5 times turning speed, usually 0.3 to 0.47 times turning speed, except in that same rare occasion mentioned before, a 90-degree contact angle thrust bearing, or in an application where the inner race is stationary. All these frequencies can be determined exactly using FreqCal, the frequency calculation program in CSI's Master Trend software. This screen is the bearing calculation screen for inputting data about the bearing. A report is then generated showing the calculated frequencies for each component of the bearing. After entering the bearing name and number, 3 other fields are important. The first is the Use Physical Data field. Toggling this to yes enables us to input the actual physical dimensions of the bearing. Secondly, specify whether the inner race is rotating. The frequencies are not the same in applications that have the outer race rotating. The frequency units can be toggled from Hertz to CPM to orders. We want to use orders so we can locate the bearing frequencies for any shaft speed. 4 pieces of information are needed for the frequency calculations. They are the number of balls or rollers, the diameter of the ball or roller, the pitch diameter, and the contact angle. The pitch diameter is the measurement across the bearing from the center lines of the balls or rollers. Tapered bearings are measured in the same way, through the center line of the rollers. The contact angle is 0 for bearings that do not have any thrust loading, such as this ball bearing. This angular contact ball bearing has a contact angle of 30 degrees. It is measured from the center line of the balls to the center of the curve. It is important to know the exact contact angle because